Trigger integral. Okay, so in this video we are basically integrating a combination of trigonometric function and complementary error function. So if you don't know about complementary error function, so basically our c of x is just 1 minus r of x, and r of x is basically the error function. And what this means is basically integral from 0 to infinity of Gaussian integral is root pi by 2a. Now if it's just from 0 to x, it will be slightly less than root pi by 2. So what we can do is we can write root pi by 2 and then times some slight error. Yeah, because this is not equal to root pi by 2. So this error is known as error function. And so in this way it's defined as r of x is equals to 2 by root pi integral from 0 to, okay, and one mistake is basically, let me write this variable as y, let me not make the same, so this will also be y. Yeah, so basically this will be r of y, and so let me make this a y as well. So r of y will be integral from 0 to y of e to the power minus x squared dx. Now I think you understood the constant error function, and 1 minus this is just the complementary error function. And that means if we do 1 minus this, we will just get 2 by pi of integral from, sorry, not 2 by pi, it's 2 by root pi. 2 by root pi integral from x to infinity of e to the power minus x squared dx. Okay, so now you have these definitions and we are good to begin. So first of all, let's simplify this by assuming y as x square. Okay, and that gives us y to the power 1 by 2 is equals to x, and 1 by 2 y to the power minus 1 by 2 dy as dx. So with this we have integral going from 0 to infinity sine of y complementary error function of y to the power 1 by 2, and dx is 1 by 2 y to the power minus 1 by 2 dy. Okay, so if there was not this y to the power minus 1 by 2, we could have tried with integration by parts, but this is really making our task difficult. So for that, what we can do is we can basically introduce a over here, complementary error function of a y to the power 1 by 2, and then differentiate. That gives us y to the power 1 by 2 over here, and it cancels out. Also, this simplifies in quite a nicer way. So let's do that. Let us define I of a as 1 by 2. This goes out in the integral from 0 to infinity of sine y, and then our complementary error function of a y to the power 1 by 2 times y to the power minus 1 by 2 dy. Now if we differentiate this, this is gonna get cancelled out. Let's differentiate this with respect to a, and we get 1 by 2 integral from 0 to infinity of sine y. And now if we differentiate this, what do we get, you think? What do you think we will get? Basically you can see this from the definition of the fundamental theorem of calculus itself. So if you are differentiating, let's say from 0 to a, let's say a of f of x dx, yeah, and this differentiation is with respect to a, then in that case this will just be f of a. Yeah, basically you get integral of f. So what happens in this case is basically you get an integral of f, and we have capital F of a minus small f of capital F of 0. Yeah, now capital F of 0 is just a constant, and if you differentiate this now, you get small f of a. Yeah, So that's what we will use over here as well, since this has an integral definition. Yeah, so that's why uh, what we will get is uh, 2 by root pi, and then uh, this is 1 minus the integral. Yeah, is it? Yeah, 1 minus this integral of r of x. And so from this we get minus, and then r, the derivative of this function will be just e to the power minus in this variable a y to the power 1 by 2 squared. Yeah, and then uh, now differentiate this with respect to a, and so we get y to the power 1 by 2 as constant, and this is already there as constant dy. Now these do cancel out, so we have I dash of a is equals to 1 by 2 integral from 0 to infinity. Also we have, oh, what happened? Okay, okay, so we have 2 by root pi over here. This integral is from 0 to infinity, and then sine y minus e to the power minus a square y dy. Now take the minus sign outside, and we have minus 1 by root pi integral from 0 to infinity e to the power minus a square y sine y dy. Now you can use a famous like integration formula. Yeah, this one is doable because you know the integration formula for e to the power ax sine bx. Yeah, dx. Before that, let me cross this out because I think this is gonna give me notifications. Okay, now you know that its integral will be e to the power ax. Oh, let it be by a square plus a b square, and then a sine bx minus b cos bx. We know this. Yeah, if we use this over here, we get minus 1 by root pi, and then e to the power minus a square y by a square plus b square, so e to the power 4 plus 1. Yeah, and then minus a square sine y minus b is 1 cos y, and this is from 0 to infinity. So we have minus 1 by root pi, I dash of a is minus 1 by root pi, and then this is at infinity it goes to 0, minus at 0 this is 1 by 1 plus a to the power 4. Over here this is 0, this is minus 1. Yeah, so we have I dash of a is equals to minus 1 by root pi times this is 1 by 1 plus a to the power 4. Now we know that I dash of a is just di by dA, so take dA to other side, minus 1 by root pi 1 by 1 plus a to the power 4 dA. Now integrate both sides. Yeah. Now this is a pretty standard integral, and it does have a pretty standard approach as well, but that might look a bit complicated, but yeah, that is what it is. So let me show you how do we integrate that function. So let's say we have integral of 1 by 1 plus t to the power 4 dt. So the approach is quite different. So first of all, you divide numerator and denominator by t square, and you get 1 by t square by t square plus 1 by t square. Okay, if we differentiate by t square. Now the thing is this thing over here can be written as t plus 1 by t whole square minus 2, or t minus 1 by t whole square plus 2. Yeah, you can see that from the expansion that this is t square plus 2 plus 1 by 2 whole square, so 2 to cancel out, here also 2 to cancel out. And we can use this thing in the numerator. So how? Because its derivative will just be 1 minus 1 by t square, and its derivative will be 1 plus 1 by t square. Yeah, so that's why what we can do is, if we add both of them, we just get, okay, not add, if we subtract this thing from this one, what we get is 2 by t square. Yeah, so we can have both of the terms and then write them in this form. So what we can do is, we can first introduce 1 by 2 over here. Now this is 2 by t square. Now write it as 1 plus 1 by t square minus 1 minus 1 by t square. And I think you have already understood why I have done that. Yeah. So and after this I can like separate the denominator. Yeah. Now what am I gonna do? I'm gonna write this in this form. Sorry, over here I need this thing. Yeah. In numerator we have this form, so I will make denominator in this form. Over here I will make it in this form. Okay. So now let me do that. 1 by 2 integral of 1 plus 1 by t square, and then t minus 1 by t whole square plus 2 minus 1 minus 1 by t square. So this is t plus 1 by t whole square, and let me cancel this, all of this. These are just disturbing. Okay, now it's fine. Okay, and let me cancel this one as well. Okay, so now we can easily integrate this now, because the derivative of this thing is just over here and derivative of this thing is also over here. So I can let this as y and there will be dy. I can let this as y and there will be dy. So I can write this as now 1 by 2 plus y square. So that's just 1 by root 2 tan inverse y by root 2, and y is t minus 1 by t by root 2 over here minus minus 2. I missed the minus 2, sorry for that. Yeah, now this is a formula for tan h inverse x. So 1 by root 2 tan h inverse y by root 2. Yeah, and yeah, this is the solution for the integral, and this was a pretty standard approach. So no, just know this. Now I have I equals to, there are other approaches as well. I think you can check that there is one brute force approach by BPRP. You can check that on YouTube as well. Now this is 1 by 2 root 2, and then tan inverse t minus 1 by t by root 2 minus tan h inverse t, oh this is t, sorry for that, t plus 1 by t by root 2. Yeah, and then plus c. Now our job is to find the plus c. Yeah, so for that you need to notice something, that you need to notice that I of infinity is actually 0. And how will you notice that thing? Basically, if you go to our initial integral over here, if we have a as infinity, we know that orf c of infinity is just 0, because orf c of x is integral from x to infinity. Now orf c of infinity is integral from infinity to infinity, and if both of them are same, the integral is just 0. That's why orf c of infinity is over 0, so over integral will be 0. That's why I can say I of infinity is 0. Now if I put this is in fact a, okay, so I changed a to t, it doesn't matter. So now I will find I of infinity, and that will be minus 1 by 2 root 2 pi, and over here I have infinity minus 0, so this is pi by 2, tan inverse infinity is pi by 2, minus this is tan h inverse infinity is 0, because tan h inverse x is defined as 1 by 2 ln of x plus 1 by x minus, sorry, not x plus 1, x minus 1 by x plus 1, and we know that at infinity we have ln of 1, that's 0, and so plus c. You can see that now c is just, this is also 0, so that's why c is just pi by 4 root 2 pi. Yeah, you can see that c is just pi by 4 root 2 pi. Okay, now with that we have I of t as minus 1 by 2 root 2 pi, yeah, or tan inverse or t minus 1 by t by root 2 minus tan h inverse t plus 1 by t by root 2, and the c is plus 4 pi by 4 root 2 pi. Now our required integral is when a is 0, yeah. If sorry, a is 1. If a is 1, we have our required integral. So let's substitute a as 1 now. We substitute a as 1, or t as 1 over here. We have minus 1 by 2 root 2 pi, and this is tan inverse 0 is 0, minus this is tan h inverse 2 by root 2, so this that is tan h inverse root 2 plus pi by 4 root 2 pi. Now we can take the LCM. This minus minus will also be plus, so that will be 4 root 2 pi, that is 2 tan h inverse root 2 plus pi. Now tan h inverse root 2 is the negative of cot h inverse, that's why we have pi minus 2 cot h inverse root 2 by 4 root 2 pi, and that's the answer. Pi minus 2 cot h inverse root 2 by 4 root 2 pi. So if you have to talk about the flow of this integral, what did we do? First of all, we saw the definition of complementary Euler function, and then we saw that if we introduce a new variable a, that makes it somehow easier because the term cancels out, and then the integral was simplified a lot, and then we use the standard formula of e to the power ax sine bx, and then this was another famous integral which can be solved in this way. After that we found the constant out, and then we solved it. So hope you enjoyed the solution, and yeah, thanks for watching. Look forward to seeing the upcoming videos too.